Hi everyone, myself Anusree. I'm currently working as assistant professor at Sankar Memorial SNDP Yogam Arts and Science College, Kerala, India. My current research work is based on single-layered Ruddlesden-Popper phases, especially on magnetic phases. So today the title of my talk is Magnetic Glassy State in the Single-Layered Ruddlesden-Popper Phase, PrCaFe 0.5Co0.5O4. This is a iron and cobalt-based Ruddlesden-Popper phase. So when I say layered perovskite, everyone might be familiar with the AbO3 perovskite structure. Apart from AbO3 compounds, we have many layered perovskite structures such as Ruddlesden-Popper phase, Dion-Jacobson, Aurevillis, etc. So as you can see from the structure given here, the difference between perovskite structures and the layered perovskite structures is that along the C-axis, there is no connectivity of the octahedra in layered systems. So when the connectivity is lost along the C-axis, this can lead to various properties which are entirely different from those of the perovskite structures. Currently, my work focuses on Ruddlesden-Popper phases. So I'll move on to Ruddlesden-Popper structures. So for different values of n as shown here, we can have single layer Ruddlesden-Popper structure, double layered, triple layered, etc. And when n tends to infinity, we'll get the normal perovskite system. So as you can see, currently my work is focused on single layered Ruddlesden-Popper phase, that is K2BO4 type structure. So as the unit cell is represented here, we can see that in between two perovskite blocks, we have a single perovskite layer in case of a single layer system. Since there is no connectivity of the octahedra along the C-axis, these Ruddlesden-Popper phases are actually quasi-2D layered perovskite systems. And various properties such as superconductivity, multiferroid property, charge and orbital ordering were reported in Ruddlesden-Popper phases. They're also used in electrochemistry and they're used as microwave dielectrics as well. So the main point is we can do chemical substitution in the A and B side so that we can control the properties. As there is strong coupling between the chemical stoichiometry as well as the electronic structure of these compounds. So in the current work, at the A side, I have calcium and praseodymium, and at the B side, the magnetic ions, iron and cobalt are placed, and the X-ray diffraction profile, synchrotron X-ray diffraction profile is shown here. This was fitted using Rietveld refinement, and we could see that the system crystallizes in orthorhombic BMAB space group at room temperature. The crystal structure is shown here, and the ABC lattice parameters and volume values are also shown here. When it comes to magnetization properties, we have done various magnetic measurements. So first, talking about the thermal evolution of magnetization, we could observe a magnetic peak around 25 Kelvin. And another prominent feature that was observed is that there is a thermal irreversibility below the transition temperature of 25 Kelvin between the zero field cooled and field cooled curves. Magnetization was measured at two field values, that is 100 oersted and as well as 10 kilo-oersted. So to know more about this irreversibility, thermal irreversibility, we have done few other measurements. Before going to that, we have done an image curve tracing also at various temperatures. So as you can see here, the MH loop at 5 Kelvin and 50 Kelvin opens up a little bit, and that shows some values of coercivity where there was no coercivity values observed at 350 Kelvin. So this could lead to the presence of some weak antiferromagnetic or ferromagnetic interactions in the sample at low temperature. So for further measurements, we have done neutron diffraction. And the analysis of neutron diffraction says that there is no long-range magnetic ordering in the system. We have done the diffraction. We have traced the diffraction profiles at two temperatures, 50 Kelvin as well as 4 Kelvin. That is one temperature above the transition temperature as well as the below the transition temperature. But we couldn't observe any long-range magnetic ordering in the system. Further, we have done X-ray photoelectron spectroscopy measurements to know or to get some idea of the valence states of iron and cobalt in the system. So we couldn't fit the X-ray photoelectron spectroscopy peaks to one single valence state of iron or cobalt. In case of iron, we could observe Fe3 plus as well as Fe4 plus valence state with a ratio of approximately 70:30. Similarly, in case of cobalt, we could observe the presence of CO2 plus as well as CO3 plus valence states, again in the ratio approximately 30:70. Further, to know more about the magnetic transition observed around 25 Kelvin, we have done some AC susceptibility measurements. And as you can see, as the frequency varies, the peak actually shift to a higher temperature. So this rules out the possibility of any long-range magnetic ordering, and this corroborates with our observation of neutron diffraction profiles. Further, to know more about this the glassy freezing. So there is a possibility of a glassy freezing around 25 Kelvin. Since it is not a long-range ordering, there could be some short-range ordering, such as ferromagnetic or antiferromagnetic ordering in the system, leading to a glassy freezing at 25 Kelvin. So in order to know more about the nature of the glassy freezing, we have used two models, which are Vogel-Fulcher law and critical slowing down dynamics model, to fit the data observed from obtained from the AC susceptibility curves. In both the models, we could see that the relaxation time was a bit lower, or the system undergoes a slow relaxation, indicating the presence of a cluster glass state rather than a spin glass state in the material. Further, to confirm the glassy state in the compound, we have done a set of zero field cold magnetic memory measurement in the sample, and it was done under stop and wait protocol. So for as you can see, there are two curves here. One is the reference curve, and the second one is the memory curve. To obtain the reference curve, we have cooled the system to 5 Kelvin with a slow cooling rate, and thereafter magnetization was measured during the subsequent warming cycle. Then again, the sample was cooled to 5 Kelvin in the absence of any magnetic field with an intermediate halt of duration 3 hours at 20 Kelvin. That is below the transition temperature. That is how we got the memory curve. And again, the memory curve was traced or recorded during the subsequent warming cycle. So as you can see, when you take the difference of this reference and memory curves, there is a sharp memory dip present at that temperature. So this clearly confirms that the material undergoes cluster glass freezing at 25 Kelvin. Now coming to the possibility of cluster glass freezing using the magnetic ions in the sample, we can see that there are Fe3 plus and Fe2 plus compositions, Fe4 plus ions in the sample, as well as we have CO3 plus and CO2 plus ions. These ions can give rise to various ionic pair having antiferromagnetic superexchange interactions or ferromagnetic superexchange interactions as listed below. So our compound consists of a cluster glass state in which there are AFM interactions as well as FM interactions, and due to this magnetic frustration, the compound undergoes a magnetic glassy freezing. So coming to the summary, phase for PrCaFe 0.5Co0.5O4 was prepared using salt gel method. This system, the compound crystallizes in orthorhombic BMAB space group. Magnetic glassy freezing, which comes under the category of cluster glass, was observed in the material. And Computing AFM and FM interactions may be responsible for the magnetic glassy state observed. Thank you. If anyone has any questions, please feel free to ask.
Yeah, very nice talk. So please, we still have a little bit of time. So please raise your question. You can just directly unmute and talk.
Hello, ma'am. Very nice talk. I had a very basic query actually. Like, how is cluster glass state different from spin glass state? Can you like reflect on that?
Yeah, in cluster glass state, there will be spin interactions among the spins. That's why we call it as a cluster glass.
And
there is no interaction
okay.
between the spins. The relaxation time will be different. So it comes under a different range in this Vogel-Fulcher law and critical slowing down dynamics models. So based on this relaxation time value only, we could say that it comes under the category of cluster glass.
Okay, ma'am. Just a follow-up question. Like, is there any different way other than like how we find out spin glassy state and all the other some measurements? Like you showed some AC susceptibility measurements. I think they are also done to find out about the spin glass state. So
yeah, we have done AC susceptibility measurement to see if there are any long-range ordering in the material. In case if the 25 Kelvin transition was a long-range ordering, then we would not observe any shift of the peak as shown here. So here, as you can see, there is shift of the peak at this 25 Kelvin. There is a shift at various frequency values. If this was a long-range ordering, then the peak will not shift. It will be a constant peak at all the frequency values. Is it clear?
Yeah, thank you so much. Yeah.
Thank you.
Okay, very inspiring discussion. Thanks